Hi, welcome back, everyone. We are now, well, we're ankle deep in electromagnetics, you might say, and we are at Gauss's law. Gauss's law is actually one of four, so the first of four Maxwell's equations that we're going to see in our class. So let us take a look. If you recall, this is the electric field due to a point charge located at the origin. And that was the case that got us here to Gauss's law. You don't know what Gauss's law is yet, but I made reference to it in the previous video because of this example where we had spheres and we compared the electric field due to a sphere to that of a point charge located at the origin. We're going to come back to this result again later in this video. What I'd like to describe to you now is one of Michael Faraday's experiments. And chances are good that you've heard of Michael Faraday. This is not the experiment for which he is famous. We'll get to that experiment later on in the course when we talk about electrodynamics. Remember, this is first the static case. So this is a cross-section of two spheres, concentric metal spheres, where the outer one is made up of two hemispheres so that it can be dismantled and then it can be put together and encapsulate the inner sphere. In between the two spheres is insulating material, and we'll use the word dielectrics to mean insulators. That's a word we'll use quite a bit in our course, dielectrics. So the experiment goes like this. With the equipment dismantled, the inner sphere was given a known positive charge. So I've represented that with the positive signs here. The inner sphere with radius A has positive charge, and it's known. So they gave it this positive charge with conduction, for example. Then the dielectric material was placed around the sphere, and then the two hemispheres were clamped together around all of this with about 2 centimeters of dielectric material between. The outer sphere was discharged by momentarily connecting it to ground. Then, some time later, the outer sphere was removed carefully with insulated tools, and the negative induced charge on it was measured. So even though it was grounded originally, when they measured the charge, they found that there was negative charge on it. And what they found was that what Michael Faraday found was that the total charge on the outer sphere was equal in magnitude to the original charge placed on the inner sphere. And this was regardless of the type of dielectric material in between the two spheres. So there was now, remember there was a charge Q on the surface of the inner sphere, and then somehow, even though the outer sphere was grounded, there somehow moved some charge or something gave rise to this negative charge, negative Q, equal and opposite, on the outer sphere. So Michael Faraday concluded that there's some sort of displacement, was the word that he used, from inner to outer sphere, which was independent of the separating medium, that is the dielectric material. We now call this displacement electric flux. We've talked about flux before when we were talking about vectors and vector calculus and so forth, but this is what we're going to refer to as electric flux now, this situation, and electric flux is measured in coulombs, so it's the amount of charge that goes from the inner sphere to the outer sphere in this experiment. So for this experiment, the flux, which remember we use the Greek letter psi to represent, psi is equal to Q, that there was that much flux going from the inner sphere to the outer sphere. It has to be Q because there was at first zero charge on the outer sphere, and now there's negative Q. But so there was that positive Q that produced that flux. So we would say the flux is just Q positive. Now, again, the inner sphere has a radius A and the outer sphere has a radius B. If we assume that the charge is distributed uniformly on the surfaces, then the flux per area on the spheres we can calculate. So I'll use D for displacement. That's what the word Michael Faraday used. D on the surface A would be then the flux per area. So I'm looking for the flux per area. So the area of the surface area of a sphere with radius A is 4 pi a squared. And the flux per area on surface B, really this should be a negative, but for this lecture, for this example, the sign is not important. I just wanted to talk about the concept of electric flux and electric flux density. Okay, so we have those. That's the flux per area, so that's coulombs per square meter in both cases. Now if we give D a direction by multiplying it by a unit vector in the same direction of the electric field, and I've got the electric field, the electric field due to a sphere we found points radially outward, so that's the radial direction. Then we have on sphere A is Q over 4 pi a squared in the radial direction, and B is the same, although maybe negative, but again we're avoiding the negatives for right now. D, since it's the electric flux divided by square meters, is called the electric flux density and is a vector. D is again for displacement. So in this experiment, the flux density through an imaginary sphere. So let's talk about an imaginary sphere that I've got in dotted lines in between the two spheres of radius capital R. So here capital R is greater than A, inner sphere, and less than B, the outer sphere. So we can imagine surfaces now, and we can imagine the flux and the flux density through a sphere of radius capital R. Even though it's not there, okay, we can imagine what it is. And the flux density, electric flux density through that sphere would be Q 4 pi capital R squared, still in the radial direction, right? Now let the inner sphere of radius A have a radius that approaches 0 while still retaining the charge Q. So we can make the sphere as large or as small as we want. So let's shrink it down to a point charge so that it still has the charge Q, but its radius becomes 0 or very close to 0. The flux density, R meters away then, that's this thing here, remains unchanged. It will remain unchanged as we shrink the sphere. There are 3 reasons that it remains unchanged. First of all, the flux density is still Q. Because that Q will still be displaced to the outer sphere. So the idea is that flux still has to pass through our imaginary sphere of radius capital R. And also, the electric field lines that I've drawn in red, they're still normal to the surface, right? We're just shrinking the inner sphere. So the E field lines are still normal to the surface. And a sphere r away still has area 4 pi r squared, right? That's not changing. Our sphere has area 4 pi r squared. So remember, this was the limit as a goes to 0. We're shrinking that inner sphere. All of these things are still true. And so the electric flux density through R would remain the same. Now, if we compare our result then, capital D, with the electric field due to a point charge, well, they're very similar. And we see that D is equal to epsilon naught, the permittivity of free space, times the electric field. Right? That's a nice, easy relationship there. And so we've got a vector on the left and a vector on the right. So this is a vector equation, and of course, the permittivity of free space is just a constant. And so our electric flux density is in the same direction as the electric field, radially outward in this case. And it might seem silly to define a new quantity to be parallel, right, to E and proportional to E. You know, why don't we just use E? But we like using D, the electric flux density, because of two reasons. It's independent of the medium. Let me write that down. I'll explain that in a second. Of the medium. The electric field depends on this permittivity of free space. So if we're in free space, you know, outer space, or air actually has a permittivity that's close to free space. So if we're talking about an electric field in air or in outer space, then yeah, we've got electric field there, and we can use epsilon 0. But if we have a different medium, like water, for example, or you know, steel or something, the permittivity changes. Epsilon 0 will become some different epsilon. But in this case, when we're dealing with D, the epsilons drop out. And so that's what we mean by independent of the medium. That's why we like electric flux density. And then two, the second point I want to make here, is that we're interpreting, it has a different interpretation. We're interpreting it as a flux density instead of a force field. So as a flux, right, instead of a force field. So sometimes it might be convenient to think of this thing as a force field, in which case we would use E. Sometimes we might want to think of the flux, in which case we would think of D. All right, now I'm going to erase some of this. Again, feel free. Pause the video if you like. Now let's get to Gauss's law. Gauss's law feels good to write because you get 3 S's in a row there. All right, now imagine any closed surface. So we're not going to talk about spheres anymore, containing any charge distribution. So let me give you one. Let me just draw some random kind of thing. All right, here's a surface. So it's three-dimensional, hard to draw, but it's three-dimensional. I'll represent kind of a curved surface there, and we'll call this surface delta S because it's part of a larger surface. And then let's say that this surface is enclosing, remember it's a closed surface, it's enclosing so much charge. And those charges, that charge could be from point charges, or that charge could be from a continuous distribution, as we've now talked about many times. So if I want to consider the flux through just this very small incremental change in surface. So this would be the flux crossing or passing through delta S. Well, you can imagine that these charges, or this charge, if it's a distribution, creates some sort of electric field, and maybe and the electric field is proportional or in the same direction as the electric flux density. So maybe that goes out like this. So here's the electric flux density. And normal to that surface maybe is here. This is the normal to that. So remember the surface vector? The surface vector has an orientation that's normal and outward going. So that's my normal to that little piece. And so this shorter green arrow, that would be the normal component. That would be the normal component of D. And that makes an angle theta. Recall what we used to say about flux, and I gave the photo panel example of how you orient your panel towards the sun to get the most flux. Remember, it's the normal component that matters, the component that's parallel to the surface vector that matters in flux. And so in this case, the flux that's going through that little piece is D dot delta S. The two normal components match up, so they're parallel with one another, delta S and the normal component of D. And so what we end up doing here is we take the dot product. Now the total flux then, because this is only the flux through that little incremental surface area, the total flux through a closed surface is D dot ds. And what we just found from Faraday's experiment is that that is equal to Q, and I'll just put some subscripts there, enclosed. So we have a closed surface integral, and this integral is equal to the enclosed charge. That's Gauss's law. In the most general case, Q can be expressed as a volume of charge. Usually we don't deal with point charges. Usually we have an object that's charged, and it might be a line charge, it might be a surface charge, but in the most general case it's a volume charge. And so what we can do is we can write that closed surface integral d dot ds, the charge enclosed in it then is the volume charge density integrated over the entire volume. Then, here's the crux of the matter. I can apply the divergence theorem to the left-hand side. Remember that divergence theorem? It converts a closed surface integral, which we have here on the left, to a volume integral using the divergence. So now, and this V on the right side would be the volume of charged object. So now we've got the integral over the volume of the divergence of d dv from the divergence theorem is equal to, and the right side will remain the same for right now, like this, divergence theorem. And because the integrals have the same bounds over v, then we can compare the integrands. Just the integrands must be the same. So this says the divergence of the electric field density is equal to the volume charge distribution. And this is also referred to as Gauss's law. We would say that this is the integral form up here of Gauss's law, and this would be called the so-called point form of Gauss's law. And I'm going to write this down just because it's so important. This is one, our first, of four Maxwell's equations. And remember, Coulomb's law got us here. In fact, you can derive Coulomb's law from Gauss's law. And we'll do that, but for only certain examples, like the sphere example. So Maxwell's equations then encompass or account for Coulomb's law as well. Everything in Maxwell's equations, or everything in electromagnetics, is contained in Maxwell's four equations. Now, we don't have to deal with spheres and so forth. We can deal with any sort of closed surfaces. So if I have, say, a charged object that is charged to maybe 10 nanocoulombs, and I have some weird looking surface like this, and maybe another weird looking surface like this. Okay, those are three-dimensional. They have surfaces and volumes and so forth. And this thing is going to create an electric field density. Right, I don't know exactly what it will look like because it's oddly shaped, but maybe it looks like this, something like that. What we would say using Gauss's law is that this surface, call it S1, S1 has a net electric flux of 10 nanocoulombs. Why is that? Because the flux through a closed surface is equal to the charge enclosed. And that's net, by the way. That's the net flux. Why that's important, you'll see in a second for surface S2. S2 contains no charge, and as a result, any electric field line or electric field density line, any flux line that goes into the surface must leave the surface because there's no source or sink there. There's no positive or negative charge. So the ones that go into the surface are that's negative flux, and the ones that leave the surface are positive flux, and they cancel. Any flux line that goes in comes out, and so the flux through this surface is zero. Right? Nice. All right. So let's work on applying this a little bit, because this is, if you're not used to seeing these sorts of integrals, and these can be a little challenging to apply. Although you'll see that actually when you have symmetry in your problem, Gauss's law is your friend. It really will help simplify the problem when there is symmetry. So that's what we're going to do in the next video, work out some Gauss's law problems.